tend to screen each other. I mean, they cost essentially zero energy because even the core becomes free. It's a very high temperature. Okay, so can we do this? Well, what people tried this, or analogs of this, thinking about this. So maybe if you add some higher order terms, some ring, 4-body terms, and these could then be sensitive to whether locally you had a 4-pi or a 2-pi vortex, and then you could suppress the 2-pi, only get the 4-pi. You could do this, but it's not very illuminating, and it doesn't allow you to really prove that there's a phase transition. Okay, so what works is, in some sense, you take this term and you decouple it by introducing an auxiliary field. So this is the model I'm going to talk about now. For the experts, you're coupling the XY model to a Z2 gauge theory. But don't worry about that. I'll explain that if you don't know what that means. So right now, I'm just postulating this action, and I just want to explain what the action is. I've introduced a new variable, sigma, which is plus or minus 1, on every link of the cubic lattice. And then there's a term here which measures the flux, that is the product of sigma around this plaquette, and you cost energy k when that flux is minus 1. 2k, really, relative to them being all plus 1. Okay, so that's this term. And then the sigma also couples to the angles, but notice this factor of 2, and I'll explain that in a minute, with the sigma ij here. So this looks like a very strange model because I have a new field that I don't know what it is. It's not even going to be measurable in some sense. And I have put this factor of 2 that seems completely illegal because the model should be invariant that theta goes to theta plus 2 pi. So what does this mean? All right, so let me now show you that's all completely legal, and I haven't done anything. What I've really done is just rewritten this type of term, which you'll be happy with, in a more illuminating way. So let me now describe some properties of this action. Okay, so the first thing you can do is consider the case where k is small. Then you can just do a small k expansion of the partition function. You can explicitly sum over the sigma. Just do it by hand. So in fact, at k equals 0, you can see what will happen is that for every for every bond, I just have to sum over sigma of e to the sigma, I forget the j, cosine theta 1 minus theta 2 over 2. And that's going to be something like cosh cosine theta 1 minus theta 2 over 2. And now I want you to notice that this is some kind of two-body term. This is periodic in theta goes to theta plus 2 pi. But just shift theta 1 by 2 pi. Because this is an even function, it will come back to itself. So it has the right periodicity. It only depends on the angle differences. So it's basically an XY model. Any interaction that's periodic and prefers spins to be parallel is good enough. So it is basically an XY model. But this is still a two-body term, only two thetas. But once you go to higher order in k, you'll start getting terms that involve theta around a plaquette. And so you see that it's basically the same model, except I've written it in a compact way using this auxiliary binary variable. Okay, so that's point 1. Second point 1, this is what's called a Z2 gauge theory, because this theory has a gauge invariance. So I can shift theta by 2 pi eta I, and eta I is any arbitrary, either plus 1 or minus 1. And it doesn't have to be the same on every side. It can be different on different sides. So there's a binary variable on every site, plus or minus 1. And I can use it to generate a gauge transformation in which sigma ij will transform like this. And you can see that this is basically very analogous to electromagnetic gauge invariance, except you're in the case where the gauge field can only take two values, 0 or pi, not all possible angles. So this is like taking a circle, that is what the electromagnetic gauge invariance is, and just only allow 2 points in the circle. So that's why it's called Z2 gauge invariance. You can have a Zn gauge invariance, and then you'll have n points and so on. All right, so this is a Z2 gauge theory. And for the experts, it's a Z2 gauge theory with a matter field, which is this one here. So if you are thinking of using Wilson loops to distinguish phases, forget it, because there's matter fields around. But the original XY autoparameter is gauge invariant, and so this is basically just an XY model. I've just written it in this way. Okay, so yes, Sandeep?
But you can use the Z2 gauge to distinguish various phases now, at least on the torus, by asking about Wilson lines.
Yes, yeah, in the quantum system. Yeah, but you can't use the area law versus perimeter law. Yeah. Okay, but Sandeep jumped ahead a little bit, but it's okay. So why did I go through all this trouble? Well, it turns out this is exactly what's needed to count even versus odd vortices. So imagine I have an odd vortex, okay? So if I have an odd vortex, then I claim that this product around the plaquette is going to be negative. And why is that? Well, if I have a simple vortex, which looks something like this, now I have to give some values to the angles. So if I call this pi by 4, 3 pi by 4, and 5 pi by 4, and 7 pi by 4, or no, did I do that wrong? No. It's pi. Yeah, no, that's correct. That's correct. Then if I take the difference of these two and take half the angle, I get some small angle, so the cosine is +1. But there's a problem here. If I didn't have the half angle, of course, I'll get the same cosine difference. But because of the half angle, an extra contribution of cosine of pi, so there's a branch cut. And that branch cut will make this cosine of pi is -1, and it'll flip the sign. Okay, so this thing is going to be negative. So we don't want it to be negative. Well, we don't want the cosine to be negative, so because j is large. So when this becomes negative, then this will also become negative on that link. So what will happen when you minimize the energy with the j's, that here you will have sigma equals 1, sigma equals 1, sigma equals 1, and here you'll have sigma equals -1. And of course, if you put the branch care somewhere else, the sigma -1 will move correspondingly. So sigma equals -1 is where the branch cut is. But from this term now, the k comes in and saves the day. This will become negative, product of sigma on the plaquette, and that's going to cost energy then. Therefore, the 2 pi vortex is going to become more expensive because of this k term. You go through the same song and dance for a 4 pi vortex, you find it doesn't pay a price. So this term is really designed to pick out odd vortices. So from that argument, I can now tell you what this vertical axis is, just k, and there, this is the postulated phase diagram. And very qualitatively, just by waving my hands, I've said here vortices are even, and here the vorticity of the vortex loops is even, and here the vorticity is odd. And I haven't proven there's a phase transition, but at least there's a plausibility argument that something is happening in this gauge theory. Okay, roughly speaking, in terms of the Z2 gauge theory, what happened here, as we just saw, is that you have no even vortices. I'm sorry, no odd vortices. But every odd vortex was associated with the flux of the Z2 gauge field. So this is a phase where the flux is expelled, and here the flux is fluctuating. And this is what particle physics call deconfined, and physics called deconfined and confined phases. It's all a question of whether this Z2 flux is fluctuating or expelled. But if you want to use a Wilson loop to measure it, there are some subtleties that I'd rather not go into. It doesn't tell you that there's a phase transition. And this you can think of as a Higgs phase of the Z2 gauge theory, because the angle, that's like a particle which carries Z2 charge, has condensed. E to the I theta has condensed. No, don't take that seriously. This is just a schematic. Yeah, it has a more complicated shape. This is just to make the picture look nice. All right, so let me now connect to what Sandeep just said. So how can I really prove there's a phase transition? To really prove it, it turns out to be much easier to think of this as a quantum system in two space and one time dimension, and think about the spectrum of the quantum system. Now you could, if you don't like that, you can work with the classical system, but then you have to talk about strange non-local things like the eigenvalues of the transfer matrix. They will distinguish, in a purely classical language, the two phases. There turn out to be no local observables that distinguish the two phases. You have to really look at some global topological properties of the quantum system, or things like properties of the entire transfer matrix. So what is the quantum system? Well, this is in the usual trick of, now think of, instead of a 3D classical stat mech, so everything so far was just classical stat mech. Now I have 2D quantum mechanics, and the third direction is time. And what happens when you do this is that the time direction, the terms in the Hamiltonian, which were in the time direction, become certain operators that are conjugate to the variables you had here. So what happens is that the time-dependent term here is conjugate to some number operator, which is conjugate to theta, and the sigma z term in a certain gauge, you get a term which is sigma x. So anyway, don't worry about, I won't really use any of this, but that's what it is. Okay.
So the sigma x term is on a vertex, or is it on that some
The sigma x term is on a link. Oh, you're right. Yeah, this is bad notation. Thank you. This is wrong. Oh, no. It's correct. It's correct. It's on a link. On every link, there's a sigma x. Only this thing goes around. This one doesn't. I've chosen a gauge where the gauge field on the time links is 1. It's what's called unitary gauge. It's a unitary gauge. All right.
So it's not like the Kitaev.
No. This is I'll mention Kitaev in a minute. This is not just a pure Z2 gauge theory. It's a Z2 gauge theory with matter, but still all of that part.
The Z2 part is not called.
No, it's not solvable. This model has a confinement transition, which Kitaev does not. Kitaev only describes one phase. I'm trying to describe 3 phases. Yes, there is. You can impose it if you want, but you can also ignore it if you want. It won't change much, I think. He's talking about the Gauss law. So there's an infinite set of operators that commutes with the Hamiltonian associated with the Gauss law, but okay, I'm happy to talk about that, but probably not. So the main point I want to make here is there's a very neat way to think about topological order in this phase, is that this phase now has a new type of particle, which is stable particle, which are these odd vortices. So I told you that if you were in this topological phase, there were no odd vortices, and there was no flux. The ground state has flux suppressed. But suppose you manage to create a pi flux, well, then that object is a stable particle. It cannot decay. All the terms of the Hamiltonian conserve total flux. They only create flux +1 and -1 in pairs. So the odd vorticity is going to be preserved. And so the spectrum of the system has a new class of particles. In condensed matter physics, sometimes they're called visons, which only exist in the topological phase. And another thing about this particle, this thing that can move around, is that you cannot create it by any local operator. If you take the ground state of the system and hit some operator, you perhaps will create a Vison, two Visons, because the net flux has to be 0. And this particle is its own antiparticle. And then you'll have to take the two Visons and move them far apart. That requires some non-local operators. So, but if you're in an infinite system, you could see a particle moving around here, and nothing you could do to it could get rid of it locally, and it's completely stable. So in fact, that's behind the idea of topological protection and topological quantum computing, is that you have these super selection sectors, as Sachdev calls them, associated with the existence of these emergent particles.
This is a bound state over 2 pi vortex and ICMS.
Yeah, strictly speaking,
If two of them I could get 4 pi and no ICMS, or if
you could get both,
yeah.
I suppose. But this is there's only one stable quantum number. Right. Okay, there could be many other particles, but this particle only exists in this topological phase. So this is one way to distinguish the two phases very robustly. And it doesn't even require a gap. Okay. And finally, the other way is what many people have heard about. The most familiar way is to take the system on a torus, put it on a torus, and then what you can do is you can put that flux pi through the whole of the torus. So this is the -1s of the sigmas. They go all the way around the torus. And since this is a state with only local correlations, that flux that you put through the whole of the torus, if the system is big enough, costs essentially 0 energy. And therefore, the ground state is degenerate when the